Here we want to examine the individual events that cause the different phases of an action potential. Now, it's important to recognize that these events occur at any location along the axon, right? It's the same series of events that occur to generate an action potential at each individual segment. Now, it's also important to note that an action potential generating another action potential downstream and then another downstream from that is known as a nerve impulse. Now, if we look at one of these spots, let's start with the one closest to the axon initial segment here on the left and examine it more closely, right? If we look at the voltage graphed here, before the arrival of an EPSP, right, our excitatory postsynaptic potentials, assuming we're going to stimulate this neuron, right, we'd get EPSPs being generated on the dendrites of this neuron, leading to electrotonic current across the soma and arriving at the axon initial segment, right? But before that happens, we would be at rest, resting membrane potential. And of course, that's generated by largely by potassium leaking, but certainly the gradients are maintained by the sodium-potassium pump, and there's a chloride leak channel. And so a lot of things are going on to keep us stable. Now, once we reach the threshold of the voltage-gated channels here, voltage-gated sodium channels initially, in B, what we see, in other words, our EPSP has arrived, depolarized us to threshold, so put a little dashed line right here, right, which causes the opening of, initially, the voltage-gated sodium channels. And so we're going to get influx of these cations. That's going to result in a more positive membrane potential, the upswing of this action potential spike. It's very rapid. And it's going to reach a positive membrane potential before those channels close. And that's because the equilibrium potential for sodium is very positive. It's actually plus 60 or so, plus 65 millivolts. Now, it doesn't reach that exactly because, first of all, other ions have permeability through leak channels, but also because that channel closes. Now, the potassium channels, the voltage-gated potassium channels, are stimulated at almost the exact same moment that the voltage-gated sodium channels were. But the reason their actions are displaced is that the potassium channels are just a little bit slower. And so if we move into panel C here, we can see that our sodium channels are now closed, right? But our potassium channels are open. And that cation will now be leaving the cell, making the inside of the cell more negative again. And it does this quite rapidly, right? Generating this negativity here, generating this repolarization limb of the action potential. And it's really important that this happens, right? We want the action potentials to be very short-lived events. In fact, they are only about a millisecond, 1/1000th of a second. And the reason we want that's adaptive, is that our information is coded in the frequency, the number of action potentials per unit time. So it makes sense for them to be short-lived events so that we can pattern them through time to code the information that we want to transmit along that neuron. Now, of course, after the potassium has left the cell, the potassium channels will begin to close. Again, that's a kinetic event. They were open. They will close after a very short period of time. We do get a little bit of a hyperpolarization here. You can see it here. We become a little bit more negative than resting membrane potential, and that's simply because the potassium channels don't all slam shut at the exact same instant. And if we look over here, we have our full action potential graph, and underneath it, lined up temporal, we can see that our sodium permeability will line up with our depolarization phase, and our potassium permeability will line up with our repolarization phase, at least as best we could.